Now we're going to get into some of the more complicated uses of databases and the way that they fit into applications, starting with object relational mapping. Object relational mapping is essentially just a technique for mapping rows in a database table to objects in an object-oriented system. So you can think of the class as a definition for the table in the same way that it is a definition for an object, and the row, all of the information in the row, as the data that would be used to instantiate an object of that class. There are many popular implementations of object relational mappings, some of which come in the standard frameworks and libraries of very popular languages, including Ruby, Java, Python, C++, and many other languages. I don't know that there is a clear consensus on the best particular object relational mapping, and some languages actually have several which are used interchangeably or used by different frameworks within those languages. So for example, Python has two different very popular object relational mappings, one of which is used in the Django Web Framework, and the other is used in other frameworks. This is the basic idea behind an object relational mapping, and it has held up pretty well, but it doesn't address all of the things that we need with modern databases. That's one of the reasons why the NoSQL movement, or the non-relational database movement, has gained so much traction in the last 5 to 6 years. Non-relational databases are really trying to address something that isn't guaranteed by relational databases. So in database theory, there is a theory called cap theory that says that you can have, you should try to guarantee consistency, availability, and partition tolerance. And that is the goal of a relational database: consistency, availability, and partition tolerance. But speed of access, especially for large data sets, latency, is not guaranteed under cap theory. And non-relational databases are designed mostly around improving latency at the cost of some consistency, availability, and partition tolerance. So how are non-relational databases doing that? Well, there's lots of different implementation mechanisms for modeling data in a non-relational database. The three most popular are key-value stores, document-based databases, and graph-based databases. Okay, so there are lots of different ways that you can organize data around its inherent structure. If you're not doing it in a relational fashion, you probably are going to be doing it in some other fashion similar to one of these three: key-value stores, document databases, and graph-based databases. Here's some popular implementations of NoSQL databases. MongoDB and CouchDB are document store databases. Bigtable, which is a Google database, does column stores. Cassandra is an open source kind of clone of that for the Apache Foundation. Redis is a very popular data structure store, which is similar to a document store. And then MemCacheDB is a very popular key-value store that specializes in high speed of access, so very low latency access for keys and values that are stored associated with one another. Okay, so it's also worth talking about serialization, marshalling, and some data exchange formats, because this is another one of those more complicated uses of databases that are just ubiquitous, impossible to avoid in practice. Both terms refer to storing objects in a memory format that can be stored to disk or stored for transit, but not intended to be accessed in the same way that a database would access the data. So serialization techniques are supported by a lot of programming languages. There's a list here. Most other modern languages have some sort of a way of taking an object in memory and storing it to disk using some kind of serialization or marshalling technique. C and C++ do not support inherently serialization and marshalling. It's not a native thing, in part because they're not really object-oriented languages that allow for that kind of access. They're too low level is another way of saying it. They don't really have an easy way of identifying, oh, this was the class definition and this is how it was related to everything else in the system. But you can use similar techniques. It may not be a true serialization. There are other ways, of course, of storing binary data from memory in those two languages. It just wouldn't be considered serialization and marshalling. Now, you don't really want to use this as a data store, right? You should not be using serialization and marshalling as a database. Better solutions are available for this sort of procedure, but you do sort of see these things used in common situations, essentially where you have very short-term storage requirements, and the overhead of the database would be overkill for the kind of storage that you're interested in. Another important goal of data exchange is having a transfer format that can go from one system to another accurately and quickly without having to have the overhead of a database. There are many formats that are used for this. The four most common are JSON, which is a JavaScript object notation. You can sort of think of this as the serialization mechanism for JavaScript. CSV, comma-separated values. This is very similar to a database in the sense that you probably would have multiple CSV files, one for each table, but it doesn't actually give you all of the guarantees of access that a DBMS would. So it's not truly a database in the sense that it's really better suited as a data exchange format so that you can bootstrap the database that you're trying to build based on CSV files. YAML, which is a human-readable data serialization format, very commonly used in languages like Ruby and Python, and then XML, which is an extensible markup language that is actually very comparable to databases in some ways. It has its own query engine called XPath, and very different from databases in other ways. It's extensible in a way that's kind of difficult for a database to pull off at the user level. Normally, I would have a group activity at this point for people to identify which format would be most appropriate for storing data in your project groups. Which data would you most likely need to exchange from one organization to another, one system to another from your project groups, and what format would you use for that data exchange? Essentially, of the various options listed here, which format would be most appropriate. Again, I'm not really in a position to do that now, given that we are not actually physically present and you can't have these discussions, but I would encourage you to think through these things on your own to try and come up with a list and a good rationale for why you think that's a good answer to these questions.